Section 2 here, the dimension of a vector space. Sounds Twilight Zone-y. Theorem 3. So a vector space V has a basis B. Then any set in V containing more than n vectors must be linearly dependent. Think about why that's the case, right? If it's a basis, that's the exact number of vectors that we need. So adding any more automatically makes it a linear combination, by definition, linearly dependent. So if a vector space V has a basis of n vectors, then every basis has n vectors, right? So that previous example from section 1, we talked about those 3 vectors were basis for R3. In fact, any basis for R3 will contain exactly 3 vectors, right? So if V is spanned by a finite set, V is finite dimensional, and the dimension of V, which is denoted dim of V, right? You can see that sort of that pattern in this course, right? It's always the first 3 letters. Dimension of V is the number of vectors in the basis for V. And of course, the dimension of the 0 vector space is 0. So the dimension of Rn, of course, would be what, right? Dimension of R3, 3, dimension of R4, right? This would be n. Be careful with this one. So this is, remember, P sub n is a polynomial of degree n. So if we look at, let's say, P sub 3, right, we have a constant C0 plus C1x plus C2x squared, degree 3 plus C3x cubed. So 1, 2, 3, right? We have 4 entries here. So the dimension is actually n plus 1 here. Let's find a basis for this and state the dimension. Okay, so S and T are real numbers. Splitting this up into the 2 vectors, V1 and V2, right? 4 minus 3, 0 for S, and then 0, 0 minus 1 for T. Notice that the basis is V1, V2, and the dimension is 2, right? There's 2 vectors here. Okay, there's 2 vectors here. Let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be expanded to a basis, right? And the dimension of H, of course, is less than or equal to the dimension of V. Given 2 linearly independent vectors in R3, you can, of course, expand that to be a basis for all of R3 if you add 1 more linearly independent vector. And so putting it all together, we get this thing called the basis theorem. So V is p-dimensional vector space, p greater than or equal to 1. Any linearly independent set of exactly p elements is automatically a basis, right? Because it has the right number of elements and it's independent. Any set of exactly p elements that spans V is automatically a basis, right? So in other words, if you have the right number of items, you only need to show the set's linearly independent or that the set spans. Why would I care about that? Because oftentimes, not really, sometimes, linear independence is easier to show. Okay, so you would get that spanning piece for free. Recall the dimension of the null space of A, right? All those things get mapped to the 0 vector, is the number of free variables in the equation x equal to 0. And the dimension of the column space is the number of pivot columns, right? You see a relationship here? So here we're going to find a basis, state the dimension, right? We have A, B, and C. There should be 3 vectors there. Find the dimension of the null space and column space, right? Again, that's pretty straightforward, boiled down to pivot positions versus not, free variables versus not. And then if you want to look this up, these are pretty interesting, actually. They do have some other applications. Okay. And then, of course, the homework is very similar. We have dimension, null space, and column space for the given matrix A. And then we're back to these little polynomials.